Welcome to Data Mining, Machine and Deep Learning. Artificial intelligence is the broadest category, encompassing any system that mimics human intelligence, including robot programming, search algorithms, and decision-making based on logic. Within AI, we find machine learning, a powerful subset focused on developing systems that learn from data and improve over time. Deep learning is a specialized branch of machine learning that uses multi-layered neural networks to model complex patterns. Deep learning is behind technologies such as image recognition and speech-to-text conversion. Within deep learning, we have large language models, or LLMs, such as ChatGPT, BERT, and T5. These are trained on massive data sets and are capable of understanding, generating, and reasoning with human language. Machine learning is the science and the art of programming computers so that they can learn directly from data without being explicitly programmed with every rule. Supervised learning models include decision trees, support vector machines, and random forests. In contrast, unsupervised learning works without labeled data. Here, the goal is to discover patterns, groupings, or structure within the data itself, using techniques like clustering, association rule mining, or dimensionality reduction. Examples include k-means, PCA, and DBS-SKIN. Semi-supervised learning bridges the two, combining a small amount of labeled data with a large amount of unlabeled data to improve learning efficiency. Reinforcement learning is a different approach altogether, where an agent learns by interacting with an environment, making decisions and receiving rewards or penalties based on its actions, much like learning through trial and error. When we compare machine learning and deep learning to traditional algorithms, there are clear advantages and disadvantages. On the positive side, ML and DL automate decision-making by learning directly from data, rather than relying on hard-coded rules. ML models learn and predict. Learning can happen in two ways. In batch learning, the model is trained all at once using all available data, and this process is typically done offline. In online learning, the model updates itself gradually as new data arrives, learning incrementally through individual instances or mini-batches. When using models, we distinguish between instance-based methods, which compare new cases directly to stored examples, and model-based methods, which build a predictive model during training and use it to make fast decisions. In supervised learning, the machine is trained using labeled data. That is, data that already includes the correct answers. Through this process, the algorithm learns to associate inputs with the correct outputs. The labeled dataset shown here identifies shapes like hexagons, squares, and triangles. The model is trained to recognize patterns. When new test data is introduced, it can predict which shape it most likely represents. Supervised learning techniques are generally divided into two main types: regressors and classifiers. Regressors are used when the goal is to predict a continuous outcome, such as house prices or heights. Here, the output variable is a real number, like a dollar amount or a measurement. Classifiers are designed to categorize information into distinct groups. They predict distinct labels, like whether an email is spam or not. Classification can be further divided into binary classification, where only two possible outcomes exist, and multi-class classification, where there are several possible outcomes. Unsupervised learning is a branch of machine learning where algorithms are designed to identify patterns and relationships in data without the use of predefined targets or labels. No ground truth or prior instruction is guiding the algorithm. Instead, the machine sorts, organizes, and interprets the data, searching for natural structures or groupings. The goal is to find hidden patterns without prior knowledge. For example, given a set of images, an unsupervised learning algorithm can group similar photos, even though it was never explicitly told what a dog or a cat is. It is a powerful tool for data exploration, anomaly detection, customer segmentation, and more. The model may find patterns, but interpreting those patterns meaningfully often still requires human insight. In unsupervised learning, there are two main categories of algorithms: clustering and association. Clustering focuses on organizing a set of data points into groups or clusters where members of the same group share similar characteristics. The main goal is to group similar observations together so we can better understand the structure of the data. For instance, businesses often use clustering to segment customers based on purchasing behavior, allowing for more targeted marketing strategies. On the other hand, association rule learning seeks to uncover interesting relationships between variables in large datasets. Rather than grouping similar data points, association looks for patterns that link different attributes together. A classic example is market basket analysis, where customers who purchase a new house are often found to buy new furniture shortly afterward. Developing an effective machine learning model follows a structured process. It begins with data preparation, where exploratory data analysis and feature engineering refine the input data. Then, during the training phase, the model learns to map inputs to outputs by minimizing the error between its predictions and the actual results. Optimization comes next, involving hyperparameter tuning to further enhance model accuracy by fine-tuning key settings. The model enters the testing phase, where it is evaluated on unseen data to assess its ability to generalize beyond the training set. If performance remains strong across both training and testing datasets, it signals that the learning process has been successful and that the model is ready for deployment. This cycle ensures models are not only accurate, but also robust and reliable when facing real-world challenges. Deep learning is a specialized branch of machine learning that focuses on neural networks with many interconnected layers. These networks are designed to automatically learn representations of data by progressively extracting higher-level features from raw inputs using hierarchical structures. Unlike traditional machine learning, where feature extraction often requires manual effort, deep learning enables the model to discover complex patterns on its own. This makes deep learning especially powerful for solving sophisticated tasks such as image recognition, natural language processing, speech recognition, and autonomous system control. Its ability to handle vast amounts of unstructured data and uncover intricate relationships has positioned deep learning at the core of modern artificial intelligence advancements. The history of neural networks stretches back to 1943, when McCulloch and Pitts developed the first computational model of a neuron, laying the theoretical foundation for artificial intelligence. In the 1980s, major progress was made when researchers like Rumelhart, Hinton, and Williams popularized the backpropagation algorithm. Backpropagation allowed neural networks to learn from errors and adjust themselves, greatly improving their performance. In the 2010s, breakthroughs in deep learning emerged, driven by large-scale neural networks, the availability of massive datasets, and advances in computational power. Neural networks come in different types, each specialized for certain tasks. Convolutional neural networks, or CNNs, are designed for image and video processing by capturing spatial hierarchies in data. Recurrent neural networks, or RNNs, are ideal for sequence prediction and speech recognition, as they can retain information across time steps. Generative adversarial networks, or GANs, are powerful in unsupervised learning, where two networks compete against each other to generate realistic images or data. Deep learning has revolutionized a wide range of industries by enabling machines to perform complex tasks with remarkable accuracy. In image and video processing, it powers object detection, facial recognition, and surveillance systems. In the automotive industry, deep learning is critical for autonomous vehicles, helping them interpret their surroundings and make real-time decisions. Speech recognition technologies like Siri and Alexa rely on deep learning to understand and respond to human language. In healthcare, deep learning models assist in diagnosing diseases such as cancer by analyzing medical images. There is a strong dependency on data. Machine learning and deep learning models require large amounts of high-quality, representative data to learn effectively. Without sufficient or diverse data sets, models can struggle to generalize. Computational cost is a significant challenge. Training deep learning models demands substantial computational resources such as powerful GPUs and large memory capacities, making the process expensive and resource-intensive. Another major challenge is interpretability. While machine learning models like decision trees are relatively easy to interpret, deep learning models are often complex and function as black boxes. This makes it difficult to understand why a model makes specific predictions. Finally, overfitting remains a persistent concern. A model may perform extremely well on the training data, but fail to generalize to unseen data, resulting in poor real-world performance.